For decades, astronomy relied on a single powerful assumption. Earth represented the absolute peak of biological potential. If we were going to find life elsewhere, we needed to find a planet with the same mass, orbiting the same type of star, at the same distance. That perspective shifted in 2009 with the launch of NASA's Kepler Space Telescope. This graph shows Kepler's primary hunting technique, the transit method. As a planetary body crosses in front of its host star, it blocks a tiny fraction of the light, creating a measurable dip in the star's overall luminosity. Over its 9-year mission, Kepler observed over 500,000 stars. Instead of finding a galaxy filled with neat, orderly Earth replicas, the data exposed a chaotic universe packed with extreme, bizarre environments. Take PSR J1719-1438b. This exoplanet orbits a rapidly spinning, dense neutron star. The star's intense magnetic field stripped away the planet's outer layers, leaving behind a core composed largely of crystalline carbon. It is essentially a massive diamond, 5 times larger than Earth, suspended in space. Or HD 189733b, a gas giant located 63 light-years away. It sits so close to its parent star that it is tidally locked, meaning one side constantly bakes at 2,000 degrees Fahrenheit. The intense heat combined with 4,500-mile-per-hour winds creates an environment where liquid glass rains entirely sideways. The sheer variety of these intense environments proves the universe does not prioritize Earth-like conditions. Planetary scientists are now looking at an entirely new set of criteria for what makes a world habitable. We don't need to cross interstellar space to find environments that break traditional rules for life. Some of the most compelling candidates exist right here in our own solar system. Consider Saturn's largest moon, Titan. It sits almost 1 billion miles from the Sun, making it a dark world that receives only 1% of the sunlight we get on Earth. Yet, despite an average surface temperature of -290 degrees Fahrenheit, Titan features an active climate. In fact, it has stable bodies of liquid on its surface, complete with rainstorms, flowing rivers, and deep oceans. Because of the extreme cold, water on Titan is as solid as rock. The lakes and rivers flowing across its surface are instead composed of liquid methane and ethane. Deep beneath that frozen crust, the decay of radioactive elements generates internal heat. This warm core bakes the moon from the inside out, turning Titan into an active organic chemistry laboratory. The biological potential here is high enough that NASA is launching the Dragonfly mission in the 2030s. They are sending a nuclear-powered quadcopter to fly across Titan's dunes and sample the landscape for complex organic molecules. Titan proves that a planetary body doesn't need a hydrological cycle to be active. Exotic chemical seas operating in a deep freeze can provide a perfectly viable foundation for biological evolution. When we look back out at distant star systems, we do find rocky exoplanets with vast amounts of liquid water, such as K2-18b, or the planets in the TRAPPIST-1 system. These worlds sit comfortably in the habitable zones of their host stars, where temperatures allow water to flow. But their physical structures are vastly different from what we see at home. Many of these planets are engulfed in thick envelopes of hydrogen gas. Below that gas, any global oceans would be subjected to millions of bars of pressure. This presents a biological challenge. Water is abundant across the galaxy, but the crushing atmospheric pressure on these massive ocean worlds could destroy any complex organisms as we currently understand them. However, biology is resilient. Here on Earth, we have extremophiles, like the microscopic tardigrade, that can survive inside boiling liquids, withstand the freezing vacuum of space, and endure up to 6 times the pressure found in the deepest trenches of our oceans. Finding an ocean on an exoplanet is only the first step. For biology to actually take hold, the atmospheric density and physical pressure must also align to support life rather than overwhelming it. Researchers have begun identifying a specific class of worlds that might offer even better conditions for life than our own, a list of 24 exoplanets currently classified as superhabitable. The first requirement for a superhabitable world is its size. It needs to be slightly larger, up to 2 times the mass of Earth. This larger mass generates stronger gravity, allowing the planet to hold on to a thicker, more protective atmospheric layer for a much longer period of time. The second requirement has to do with the star it orbits. Instead of a yellow dwarf like our Sun, a superhabitable planet orbits a K-type orange dwarf. Orange dwarfs are cooler and less massive, meaning they burn through their fuel much slower. While our Sun has a total lifespan of roughly 10 billion years, a K-type star can remain stable for up to 70 billion years. This gives potential life a massive evolutionary runway to develop biological complexity. With a thicker atmosphere trapping more heat, the average surface temperature would be about 8 degrees warmer than Earth. In fact, this world would be highly humid, resembling the dense, biodiverse tropical rainforests of Earth's ancient Carboniferous period. When we combine a massive, stable gravity well with a star that lasts for 70 billion years, Earth looks less like a pinnacle and more like a baseline for what a living world can be. Knowing the metrics of a perfect planetary habitat is a great theoretical exercise, but the data is useless unless we possess the hardware to actually observe these worlds across the void. That observational hurdle was cleared with the deployment of the James Webb Space Telescope. Here is how the Webb telescope analyzes distant exoplanets. Using near-infrared spectroscopy, it watches starlight pass through a planet's atmosphere and disperses it into a spectrum. Specific dark lines on that spectrum act like a chemical fingerprint, allowing scientists to detect colliding oxygen molecules and water vapor. Earth's atmosphere is rich in oxygen because of biological processes. If Webb detects these exact colliding oxygen signatures on a distant world, it will be our first concrete evidence of biological activity elsewhere in the galaxy. When we do finally confirm the existence of alien biology, the host environment will probably not resemble our own. The signal is more likely to originate from a microbe swimming in a freezing methane sea, or an organism thriving in the humid air of an ancient super-Earth. For the first time, we possess the technology to look past our atmosphere and discover how far life's potential extends